Okay, today we're going to talk about reaction rates. So please be following along your Chapter 10 guided notes. There's a little bit to write down with this video. So, reaction rates. We're going to introduce what a reaction rate is. We're going to talk about how reactions actually occur in this lesson. We're going to also look at factors that will influence the speed or the rate of the reaction. And so hopefully following along in your notes, you can keep up and write down all the information that you need to. Okay, so let's get into it. A reaction rate is the speed of a chemical reaction. So it's the speed of a chemical reaction. It's how fast it occurs. So I've got a couple of pictures down here. Some chemical reactions happen very quickly, like fireworks, for example, have to happen very fast. Explosives have to happen really fast, in milliseconds. But some chemical reactions can last decades, like this truck in this field here. The iron that makes up the metal of that truck is rusting or reacting with oxygen in the air. That can take decades. Tens of years. And so some are very fast and some are very slow. Reaction rates have to be determined experimentally. So we'll look at, if you want to determine a reaction rate for a chemical reaction, you have to determine it experimentally in the lab and measure how long it takes for it to occur. So how do they calculate reaction rates? Well, the average reaction rate is equal to the change in the concentration of the reactant. So these brackets here mean concentration in terms of molarity of the reactant divided by the time that the reaction takes. And so this equation right here is very similar to something that we're familiar with. If we're talking about the rate that you're moving in your car, we're pretty familiar with miles per hour. Well, it's the same thing. So if you're taking your rate in miles per hour, you're doing miles, which is change in distance, divided by per hour. So again, it's change in time. So a rate in your car is change in distance over time. The rate of a chemical reaction, we're going to take the change in the reactant's concentration over time. So it's very similar to taking the rate of speed of a car, for example. Anyway, thing to remember, a reaction rate is the speed of a chemical reaction. So let's talk for a second about how chemical reactions actually occur. And there's this thing, it's called collision theory. It has three parts. And so there's some things you need to write down in your guided notes. So let's start with what collision theory actually is. Collision theory states that atoms, ions, and molecules must collide in order to react. So that there must be some collision of the reactants in order for there to be a chemical reaction. So the molecules must collide. For example, if we had molecule A here, there's two atoms of A, and we had molecule B, and there's two atoms of B here. Well, in order for A and B, the two reactants here, they're on the left side of the arrow, so reactants are on the left side. In order for them to react, they must collide. There must be a collision between the reactants. And then you can form the product. And so we've got this chemical reaction where A plus B goes to AB. In order for you to form the product AB, A and B must hit each other. They must collide. So that's the first thing, the first step of collision theory. Second step, not only must they collide, but the reactants must have proper orientation when they collide to allow for the formation of new bonds. So this idea of them, not only do they have to collide, but they have to collide with the correct orientation. So sometimes they might collide and just bounce right off of each other because they didn't have the proper orientation. But if A and B collide just right, they will form the product. Okay? So step one of collision theory, they have to collide. Second step, they must collide with proper orientation. Here's another slide that kind of builds on that idea of having proper orientation. Okay, so if we're looking at this chemical reaction, we've got carbon monoxide plus nitrogen dioxide goes to carbon dioxide plus nitrogen monoxide. So here's my reactants. They're on the left side of the arrow. This is carbon monoxide, and my nitrogen dioxide is right here. Well, if you look at this collision, if the nitrogen was to hit the carbon, that's an ineffective collision. So they're not colliding with that proper orientation. Now let's look at when carbon will collide with an oxygen. So this molecule right here just kind of flips, and now the carbon hits the oxygen. Then it allows the formation of carbon dioxide and nitrogen monoxide. So you do have to pay attention. They not only have to collide, but they have to collide with proper orientation in order for there to be an effective collision. Okay, final thing with collision theory. So we've looked at the first two. Reactants have to collide is number one. Number two, they have to collide with proper orientation. And this one is number three, activation energy. So activation energy, we talked about this in the previous lesson. It is the minimum amount of energy that reacting particles must have in order to complete a chemical reaction. So it's the minimum amount of energy that these reactants must hit each other with in order to start the chemical reaction. In last lesson, we talked about these diagrams. They're called energy diagrams, where we measured enthalpy, which is heat energy, on the y-axis, and then the reaction time is on the x. But if you remember this hill here in our energy diagrams, this hill is called the activation energy. So in order for the reactants to, collide with enough energy so that they will form the products, they've got to hit with this amount of energy. It's called the activation energy. So let's say we have A and B again, and they're going to make the product AB. So our reactants are A plus B, our products are AB. If these two were to hit each other with, say, this much energy, would there be a chemical reaction? Would it be able to make the product AB? And I'm hoping that you're thinking to yourself that no, if they hit with just that much energy, it's not going to form any product. The activation for energy for this reaction is up here, so it's got to hit each other with this much energy in order to overcome that hill, this activation energy, then it will form the products. Okay. So that's the third step of the collision theory. The reactants must hit each other hard enough in order to overcome the activation energy, and then it will form the products. Okay, so let's summarize collision theory. Number one, the reacting substances, whether they're atoms, ions, or molecules, must collide. They have to hit each other. If there's no collision, there will be no reaction. Those molecules have to hit each other. They must collide. Step two, not only must they collide, but they must collide with the correct orientation. They have to hit each other with the correct orientation, or otherwise they might just bounce off of each other and no chemical reaction will occur. Okay, and then finally, step three, the reacting substances must collide with sufficient energy. So they have to hit each other hard enough, with enough energy, to reach the activation energy needed to complete the reaction. So if they just kind of glance off of each other and they don't meet that activation energy, then no reaction will occur. But if they hit each other hard enough, with enough energy to overcome that activation energy hill, then they will form the products and the chemical reaction will occur. Okay, so that's collision theory. It's going to be tested in this chapter, so I hope that you will remember these three parts. Again, they must collide, They must collide with correct orientation. And finally, they must collide with sufficient energy to overcome the activation energy. All right, and one final slide on this. So let's go through the summary of collision theory one more time. First one, they have to collide. So this reactant and this reactant, they have to hit each other. They also have to hit each other in correct orientation. That's step 2. Step 3 is that they have to hit each other with enough energy so that they overcome this hill here, this activation energy, and then it will form the products. But again, if you give it, they collide with this much energy, will they form the products? And the answer is no. You have to give it at least this much energy to overcome that activation energy barrier. Okay, reaction rates. Let's see if I can move this out of the way. It just says reaction rates here. Let's look at this graph for a second. Okay, again, whenever you have a graph in science, the first thing you should do is look at what's reported on the axes. On the y-axis here, we're measuring concentration. So as concentration increases, you move higher. On the x-axis, we're reporting time. So as the reaction takes place, we're just tracking what's happening through time. Okay, well, we've got this chemical reaction here. Nitrogen dioxide, 2 moles of nitrogen dioxide, looks like it's a decomposition reaction where it decomposes into nitrogen monoxide plus oxygen. And if you look at the number of moles here, that's going to be kind of important. Remember that the moles is given by the coefficient out in front. So there's 2 moles of nitrogen dioxide decomposed to form 2 moles of nitrogen monoxide plus 1 mole of oxygen. Okay. Well, let's look at how this relates to reaction rates. Number 1, reaction rates can measure the disappearance of reactants. So if you'll notice here, this is a decomposition reaction where nitrogen dioxide is decomposing and it's forming the products. So we can look at the disappearance of the reactants. So over time, this is going to disappear. Its concentration is going lower and lower and lower as the reaction proceeds. So the reactant's going to disappear. Number 2, reaction rates can measure the appearance of a product or products. So our products in this chemical reaction are nitrogen monoxide and oxygen. So if you notice, their concentrations are increasing over time because they're forming in the chemical reaction. And number 3, that reaction rates are proportional stoichiometrically. So the stoichiometry has an effect on reaction rates. So let me show you what I mean. As 2 moles of nitrogen dioxide are decomposing, 2 moles of nitrogen monoxide are forming. So if you look at how the concentration is decreasing over time with nitrogen dioxide, this one, it's kind of just the inverse of how nitrogen monoxide is forming. Because 2 moles of nitrogen dioxide are decomposing and forming 2 moles of nitrogen monoxide. But now let's contrast that to how the formation of oxygen. So as it forms over time, you can tell that it's the slope of this line is much lower. It's got a more shallow slope to it than it does the other product. How come? How come oxygen is kind of such a shallow slope, and nitrogen monoxide is more steep? And the answer lies in the stoichiometry of this reaction. There's 2 moles of nitrogen monoxide forming for every 1 mole of oxygen. And so you're going to see it appear twice as fast as oxygen is appearing. And that goes back to the stoichiometry. Okay. So let's talk about the factors that will affect reaction rates. Number one, temperature has a huge influence on reaction rates. As you might be able to kind of predict, if you increase the temperature, it will increase the rate of the reaction. So increase in temperature always increases the reaction rate. So you can make chemical reactions go faster by increasing the temperature at which the reaction is run. Now let's think about that for a second. What happens to the speed of molecules as you increase the temperature? Hopefully you're thinking to yourself, well, if you increase the temperature, those molecules move faster. And if they move faster, will they collide more often? Yeah, they're moving faster. There's more chance that they're going to collide. There's more chance that they're going to collide in a correct orientation and with sufficient energy to overcome the activation energy. So they're going to hit more often and they're going to hit harder so that there's going to be a faster rate of reaction. So increased temperature increases the rate. Always. And the opposite of that is true. If you do the reaction in a cold environment or decrease the temperature, that will make chemical reactions happen slower. And this is exactly why we have refrigerators. Refrigerators, what do? Well, they decrease the temperature. What happens to the speed of chemical reactions if you decrease the temperature? They slow down. So our food in the refrigerator will react with oxygen in the air much slower, and those reactions happen slower so we can keep our food preserved longer, so they don't go bad as fast. Okay, number two, the second factor that affects reaction rates is surface area. Okay, surface area. So here's the idea with surface area. Increasing the surface area increases the rate of the reaction. Let me show you what I mean. If you have some chemical here and it's a big cube, well, you can get it to react, but the reactants that are available to react are on the surface here. And so everything inside this cube would not be able to react until the outside surface has reacted. One thing that we can do is crush it up, increase the surface area, and now look how much more of the surface of this reactant is able to react. It happens much faster. If you increase the surface area by crushing up that reactant, it will happen much faster. Here's an example. Medications that you take. You can take the pill, a capsule, and they're designed to react with a certain reaction rate over a period of time, a long period of time. So maybe it just slow releases that medication into your body over time. Well, if you want that reaction to happen fast, we take a liquid form. Liquid form has more surface area, and it's able to react faster. And so we'll show you some examples of this in class. Okay, but again, crushing it up, increasing the surface area, increases the rate of the reaction. All right, third factor that will affect reaction rates is concentration. So increasing the concentration usually will increase the rate of the reaction. So if we increase the concentration, we will usually increase the rate of that chemical reaction. So if it's at 1 molar concentration or 2 molar, which one is going to react faster usually? Well, because there's more molecules, there's more solutes, there's more particles that are able to react. When you have more substances in the reaction, if it's at a higher concentration, usually that will increase the rate of the reaction. And so the 2 molar will usually react faster. Okay, and then final way is to increase or to influence a reaction rate is a catalyst. A catalyst will lower the activation energy for the reaction, making the reaction occur faster. So a catalyst will lower activation energy. If you remember what activation energy is, it's that hill. If we drew an energy diagram, the activation energy is this hill. The energy that these reacting substances must hit each other with in order to form the products. So what a catalyst will do will make that hill much smaller. And so now instead of having the reactants having to hit each other with a lot of energy, a catalyst can lower that amount of energy, and now there's more effective collisions that have enough energy and form the products, which makes the reaction happen faster. Okay. So a catalyst. Okay, so 4 things. Let's just review. Temperature. If you increase the temperature, reactions happen faster. Surface area. If you break the substance up and increase the surface area, you'll make the reaction happen faster. Concentration. If you increase the concentration, you will usually increase the rate of the reaction. And then there's a catalyst. If you lower the activation energy, now the reaction can happen faster because the particles don't have to hit each other with as much energy, and more of them will lead to a chemical reaction. Okay, so I wanted to show you an example of a catalyst. So let's look at how they work. First of all, going back to the definition of a catalyst is a substance that speeds up a reaction by lowering the activation energy. So a catalyst speeds up the reaction, but it does so by lowering the activation energy. A catalyst will ensure that molecules will collide in the correct orientation, so less energy is needed. So that's how a catalyst works. It ensures that the molecules collide in the correct orientation. So it makes them collide with correct orientation so that there's more effective collisions that will lead to the product every time. Okay, let me show you what I mean. But let's first look at this, an enzyme. You might have heard about enzymes in your biology class. Enzyme is a large molecule, usually a protein in the body, that catalyzes biological reactions. So these happen in our bodies. Anything that's alive needs to have enzymes in order to speed up reactions. There's just thousands of reactions that are happening inside of our cells all the time. And in order to live, those reactions have to happen very quickly. So let me show you how a catalyst or an enzyme works. So if you look down here, we've got 2 molecules, A and B, and they've got to react so that they can form this product, AB. So it looks like the reaction is just fusing these 2 molecules together, making the product. And you can imagine, you remember with collision theory, these guys have to hit each other, but they have to hit each other with correct orientation and with sufficient energy. Well, what a catalyst will do, and what an enzyme does, is it provides a surface. It kind of looks like a puzzle piece down here. A catalyst will provide a surface so that these reacting substances will hit each other in the correct orientation every time. And so instead of fumbling around and just by chance A and B hitting with the correct orientation, what a catalyst or an enzyme does is it provides a surface that helps these 2 substances hit each other in the correct orientation. And so now there's more effective collisions. You will form the product much faster if there is a catalyst involved. Okay. The difference between a catalyst and an enzyme. There's not much difference. A catalyst speeds up reactions by lowering activation energy. Well, so does an enzyme. The only difference is that enzymes happen in living organisms. So they're involved in catalyzing reactions necessary for life, or biological reactions. Like I said, there's thousands of enzymes in our body. Here's just one example of an enzyme that you've probably heard of. Some people have a hard time digesting milk. And so there's a sugar in milk called lactose. And lactose, you got to break it down or else it leads to digestive problems. And this enzyme called lactase helps the body do just that. It breaks down lactose. Well, people that have a mutation in the lactase DNA part, the DNA that makes this protein, this lactase protein, they might have a mutation where it doesn't work properly. And so they don't have this enzyme lactase. And well, now they can't digest lactose fast enough. And so it leads to digestive problems. Well, that's not a very serious problem. You can take lactase drops if you have ice cream or drinking a lot of milk. You can take some enzyme in a medication form in a drop, and that helps the body be able to break up that lactose sugar and you won't have any problems. But there's some diseases that humans have where there's problems with the enzymes that can be fatal. And if you have them, you might not even live, or you might live for a little while. But enzymes in the body are very important, and there's thousands of them. And so that's what they do. They speed up chemical reactions. Okay, let's look at some energy diagrams for a second and notice how a catalyst will influence the energy diagram that we draw. Okay, so this is an endothermic reaction. Remember from last lesson that endo means enter and thermic means heat. So heat is entering, and that's why we see our enthalpy, our heat energy here, is increasing. And that's because heat is coming in, heat energy is coming in. Well, endothermic reactions have a very high activation energy. So if you remember how to calculate it, you start from the reactants and you go to the top of the hill. So there's not a lot of endothermic reactions for this reason. They just have such a high activation energy. Well, what would a catalyst do for an endothermic reaction? This red dotted line represents what a catalyst would do. Now I wanted to point out a couple of things. A catalyst will not affect the energy of the reactants. We're starting at the same spot, but what a catalyst will do is lower the hill here. It lowers this activation energy significantly. So this hill is not as large, but we also end up in the same place. So the energy of the products, the energy of the reactants is unchanged. The only thing that changes when you use a catalyst is the height of the activation energy hill. All right, let's look at an exothermic reaction. Exo means exit, and thermic again means heat. And so we can't just destroy this much heat energy. Where is it going? Well, it's leaving in the form of heat. Okay, so that's what an exothermic reaction energy diagram looks like. But now let's look at how a catalyst would influence it. Again, we're starting at the same spot. And if we draw a line, if we use a catalyst, only thing that changes is the height of this hill. Now the activation energy is smaller. Compared to without a catalyst, the activation energy is much larger. And so that's how a catalyst will speed up reactions. Now those reacting particles don't have to hit each other with as much energy, which speeds up the rate at which you form the products. All right, practice problem number 4. It says to draw in a dotted line that would represent how a catalyst would change the following energy diagram. So here's an energy diagram. What you're supposed to do is just draw a dotted line and show me how a catalyst would change this energy diagram. So let me give you some time to try that on your own. Okay, and hopefully you tried that. And here's how I would do this. We're starting at the same spot, so you're not changing the energy of the reactants. It's still on this same line. But instead of the activation energy being so high, now the activation energy is much lower. And notice we're finishing, the products have the same amount of energy. So the only thing that changes is the height of this hill. Now the energy of activation is much smaller. And that's how a catalyst helps reactions happen faster. Okay, I think I've got just a couple more slides, and I wanted to show you an actual chemical reaction where we don't use a catalyst. So I believe that this first one here, this one has no catalyst. And this chemical reaction is the same chemical reaction, but this one has a catalyst. Okay, so let's watch them. And this is a student in this room doing, this reaction is called the iodine clock reaction. So what's going to happen is he's going to pour this solution into the graduated cylinder, and then you'll see what happens, but it changes to a different color. So it takes a second to get started, but I want you to notice when the reaction starts, how long it takes for this reaction to go to completion. You're going to start to see the reaction start down here somewhere. And it's a color change reaction. So there it starts, and notice how long it takes for this reaction to go to the top of the tube. So to get to the top of the tube, maybe like, I don't know, it took probably 15-20 seconds to get to the top of the tube completely. And so that's with no catalyst. Now let's watch the same reaction, but this time there's a catalyst involved. So again, we got to pour the substance into the graduated cylinder, but now watch and notice how long it takes for that reaction to go to the top of the tube. And I think you'll notice a drastic difference here. So it started, and then instantly, now it's already to the top of the tube, it's just happening as fast as he's pouring it in now. And so you can see with a catalyst how much faster the reaction rate is. Okay, so final slide, I wanted to just review for a second what we learned in this lesson. So did you learn what a reaction rate is? Reaction rate is the speed of chemical reactions. So some reactions are very fast, happen in milliseconds. Some reactions can take hundreds of years in order to happen. And so there's a big difference in the reaction rates for different chemical reactions. Did you learn what collision theory is? There's 3 parts to collision theory. Number 1, molecules must collide. Number 2, they have to collide with the correct orientation. And number 3, they have to collide with sufficient energy in order to overcome the activation energy barrier. So 3 parts. And finally, what are the 4 factors that will influence reaction rates? We talked about 4 things that can make chemical reactions occur faster. Number 1, if you increase the temperature, what does that do to the reaction rate? It makes it go faster. So increase temperature, increase the rate. That's number 1. Number 2 was surface area. If you increase the surface area by breaking that reactant up into small pieces, this will increase the reaction rate. Number 3 was concentration. If you increase the concentration of the reactants, you will usually increase the reaction rate. Usually makes the reaction go faster. And finally, a catalyst. If you use a catalyst, it lowers that activation energy barrier, and so it makes the reactions occur faster. So again, temperature, surface area, concentration, and the catalyst. Okay, so hopefully we learned all of those things. Before I finish the video, guys, I wanted to give you some more practice with these types of chemistry problems. So in your student workbook, there's a worksheet. It's called Reaction Rates Worksheet. Again, it's called the Reaction Rates Worksheet. Please go there. Let's get that completed. And I think it should be pretty easy after watching this video, but I hope this helps.